We're now moving on to energetics. In other words, how does a muscle get its ATP, and what are the different forms of getting ATP for muscle? When you think that there's only enough ATP in a fiber for about 8 twitches, it's crazy that you can do all the activities that you do all day and not actually run out of ATP. So how do we do that? Well, the first energy system that you would use, let's say all of a sudden the doorbell rang at wherever you're doing this work, your homework, and you're going to run down some stairs and whatever, or you're going to do this burst of quick activity. So you would use the first energy system called creatine phosphate, call it CP, also called phosphocreatine. So this is a really fast way of getting that phosphate to make ATP. We know that ATP is made by transferring a phosphate, right, onto ADP, adenosine diphosphate. So if adenosine diphosphate were present already, and we had a really fast route to getting that extra phosphate and slapping it on the ADP, we could make ATP pretty quickly. Well, that's what happens. We have this enzyme called creatine phosphokinase, and if we have just get my pen. If we have that molecule, I call it the miracle molecule. If you have this creatine phosphate and you had some ADP already there present in the muscle that you would be able to then have this creatine phosphate sort of split. I'm going to have it split down the middle, release its phosphate, attach it onto ADP, and we would end up with ATP here, which is what we want, ATP and a leftover creatine, okay, which is the piece here that was left over. That happens pretty quickly when you need a sudden burst of energy, a system that you're going to be able to make more ATP very quickly. In this diagram, you see a couple reaction of creatine phosphate and ADP. So creatine phosphate, the miracle molecule, is going to break down and leave just creatine left behind. And the ADP that was floating around then, along with the enzyme together, is going to snatch that extra phosphate and make the molecule of ATP. So this is a wonderful source of energy. Does it need oxygen? And the answer is no. So no oxygen needed. And why is that important? Because when you're dashing down to do something quickly, you really haven't altered your respiratory system. You haven't been bringing in more oxygen ahead of time to prepare for this. You just shut out the door. Okay, so no oxygen necessary. Down here, the products, how much do you make? Well, you only make 1 ATP per creatine phosphate. And that energy, the duration of that energy that it's going to give you is about 15 seconds. So do you notice it's fast, it's convenient, it doesn't need oxygen, but it doesn't last very long. This is what the molecule looks like of creatine phosphate, excuse me, but it's not something you would memorize. You can just visualize the phosphate here on this end that it's donating, but don't worry, you will never have to recognize this or write it out or anything. Okay, so rested muscle contains about 5 times more ATP due to this creatine phosphate that you have sort of sitting around waiting. It's a one-step reaction. It's faster than any other form of obtaining ATP. It's faster than glycolysis. If you remember glycolysis from other classes, hopefully, you have 1 6-carbon sugar, glucose, that's going to break down into 3 carbons, which is pyruvic acid. And in the breakdown, in the splitting of this molecule down the middle, you're going to manufacture 2 ATP. Okay, so this is glycolysis, but creatine phosphate is 5 times faster than doing this. Creatine phosphate is depleted in about 10 seconds completely. And so it's used during these bursts of activity. So if you think of the 100-meter dash, right, it takes about 11 seconds. The record is about around 11 seconds. It's going to be pretty much use your creatine phosphate and deplete it. This is the reverse CP reaction. You're going to have to, when those CP stores have to be renewed by transferring the phosphate from ATP back to creatine. So there's going to have to be ATP present, and it's going to break down to ADP while passing on that phosphate so that creatine can reload with that phosphate and form creatine phosphate again. But remember, that's going to take a while to reload that. So that's when your muscle is recovering from fatigue. And how long does it take exactly? It takes about 3 minutes. So you're not going to have any more of that creatine phosphate after you made that 100-meter dash, unless you take a 3-minute rest and then do it again. The second energy system we want to talk about is anaerobic glycolysis, when I was showing you a little earlier. Anaerobic again, so we're saving on oxygen still, and it produces lactic acid. So it was the picture I was showing you earlier. I have glucose, I'm splitting it down the middle, I'm forming pyruvic acid, and the result of that is that I'm making some ATP, okay, in this reaction. Well, glycolysis, it turns out, is going to give the cardiopulmonary system a time to increase that oxygen supply to the muscle. So it's like creatine phosphate, you ran out. Then you switch over to glycolysis and you use that a little bit even though you're low on oxygen because you haven't increased your respiratory rate or depth of breathing yet. So it's kind of like in the meantime, you're going to use that. But again, you can't maintain it for very long. You're going to maintain it for about 40 seconds. And that's going to take about 2 minutes to recover. And again, it's 2 ATP that you're generating. So there's my little stick guy running with oxygen because the oxygen didn't get here yet. And once it gets there, then you can really start making ATP. But in the meantime, we're going to use those other 2 methods. Just a few more reminders of glycolysis. Glyco is glucose, lysis is to split. And there's nothing new I want to say on this slide. Just bigger. Looking at cellular respiration, if this is the mitochondria here, in glycolysis, we're going to make 2 ATP. You need it for the muscles. Then that's going to feed into the mitochondria, and the Krebs cycle is going to generate 2 more ATP, and that's going to feed into the electron transport chain and oxidative phosphorylation, and that is what's going to make a lot of ATP for you, but by then you definitely need oxygen. Okay, you will need oxygen for that. So these other steps are the steps sort of waiting for you to get that respiratory rate up. Better picture of the mitochondria, outer membrane, inner membrane, and this is lined with thousands of enzymes to be able to make that ATP. So what about that third energy system, oxidative phosphorylation? It's going to use the glucose in the blood. It's going to use glycogen stores that are in the muscle, glycogen stores that are in the liver, fatty acids, but it has to be in the presence of oxygen. Yeah, presence of oxygen. So it's super efficient, but it's slow. So you get about 30 ATP per glucose, but it takes about 2 minutes to get going. So you can't use it for that quick dash out the door. It's going to come a little bit later. If you're out on the track, it's going to kick in after those others have used up their ATP already, their phosphates. So doing light to moderate exercise, enough can be made to keep up with the need. You're running around the track and you think, hey, I can do this forever. I can keep running here. And it's moderate exercise. So you're sort of jogging around and you will be able to have enough ATP because oxidative phosphorylation is going to kick in. That's all I'm going to say about that. Just, I want you to have a big picture idea of these different forms of manufacturing ATP. Questions always come up about training, and I really am not an expert on this at all. But if you think about how each energy system can be improved with training, you have to kind of force it, deplete it, and then repeat. Force it, deplete it, and then repeat. And so anaerobic training requires the depletion and recovery, I'm reading now, of targeted muscle groups. And so it would make sense that to deplete phosphocreatine, right? You deplete it in 10 seconds. So you would deplete it. You would either run or do some exercise that's fast and furious for anywhere from 5 to 10 seconds. And then you have to wait for 3 minutes for that phosphocreatine to rebuild. And then you would do it again. And then you do your burst, and then you wait 3 minutes for it to rebuild. So that's a way of pushing that system to become more efficient. For glycolysis, it lasts a little longer, so you would do about a minute of maximum exercise and then wait anywhere from 3 to 5 for recovery, and then push it again and go and do the minute and then rest again for 3 to 5, allowing for that depletion to sort of restock. Aerobic training, cardiovascular overload is going to stimulate increased cardiac output. So we haven't talked about cardiac output yet because this is what we talk about in the cardiac chapter. What you're doing when you're training is that you're pushing your body beyond what it does with ease. So cardiac output is how much blood you're pumping out by your heart in order to irrigate those muscles that you're exercising with. So when you overload those specific muscle groups, what you do is that you enhance local circulation. You create more of the machinery to be ready to get you that oxygen. So you create more capillary beds. You increase the number of mitochondria so that you can make ATP more efficiently. You increase your enzymes to be able to break down that fat metabolism more easily so that all of these are ready for this body that you're pushing into activity. There's also an increase in aerobic respiratory enzymes because you're going to increase that rate also, your respiratory rate. So all this is what training is about. It's about physiologically changing your body to be more efficient at the distribution of oxygen, resulting in a greater volume of ATP manufactured. And that's what you were doing when you were measuring your VO2 max in the first exercise, right? You were seeing how much oxygen you could actually utilize in order to make more ATP. Oxygen debt is an interesting concept. If you've run out of oxygen, you don't just drop on the ground. You start not using it for other metabolic pathways that are in need of oxygen at the time. So what are those? What else do you need oxygen for if it's not for the muscle to run around the track? Well, one is to replenish that creatine phosphate. You're going to need oxygen. 2 is to remove lactic acid that's there. You're going to need oxygen. 3 is you're going to partially restore glycogen stores, and that's going to be also with need of oxygen. So you're going to put those stores back in the muscle and back in the liver, and that's a process, a metabolic process that needs oxygen. And you're going to restore some of that ATP and oxidative phosphorylation. So what is happening for the untrained athlete that is out of breath for way longer, so think of your VO2 max again. For the individual who's not well trained, and it would have taken you more than 7 minutes to return to resting homeostasis, it's because you still had oxygen debt. You were still trying to get more oxygen and put it over to creatine phosphate, and then to remove some of the lactic acid, and you're going to use some of that oxygen to restore glycogen stores, right? So the debt that you owe your body still is making you still breathe at a higher intensity and depth for a longer period of time. Whereas the trained athlete got off that 3-minute step test and was almost back to resting within 2 minutes or 3 minutes or 4. See? So debt then is that, also called excess post-exercise oxygen consumption, has to do with paying back that oxygen in other parts of the body that needed it. In strength training, weight training, which is different from aerobic training, a question always comes up, and that is, do you make more muscle cells? And what you actually do is increase the diameter of fast twitch fibers by increasing the number and size of the myofibrils. So you make more myofibrils. You increase the proteins. You make more myosin and actin, but you don't make new muscle cells. You're not creating new cells. You're just sort of loading up on the ones that are there. Okay, let's stop this one now. This one's a little bit longer. Thanks for listening.